Okay, calculus and physics. Let me introduce you to, I guess, the first step that we're going to do in calculus, and one rule that is actually going to be apply for most of the calculus that we're going to do. So if you get this one down, then you're just like 70% of the way there. So the thing to be careful of, though, so we have written equations such as velocity as being the change in displacement over the change in time. So notice we use the triangle, so the delta. So this is the delta change over delta time. And this is where we're looking at across a longer distance, right? So if I'm looking at, velocity, so here's my displacement versus time graph, right? So if I have somebody that's traveling, and I want to look at how long it took them to get this far, what was their average velocity, right? I'm looking over a long time here. And the velocity may go slower or faster than this, right? So this is an average, and we're looking at changes in large values. What we're going to get interested in now is the instantaneous velocity, for instance, or the instantaneous characteristic, like acceleration. So at this particular point, this time point, whatever this is, what was the specific velocity at that time? And the calculus is going to allow us a way to do it. So we're going to have a slightly different way of writing it. So so I'm going to look at taking derivatives, or figure out the rates of change. And instead of using deltas, I'm going to be using the d over dt. And so what this is representing, so this is still representing the same idea as a delta. So this is like my change in, displacement over change in time, but the lowercase d means I'm going to be focused on a really small amount of time, right? So, and this is, the idea behind calculus is really of limits, of trying to shrink things down smaller until it gets so small it really doesn't make any difference. Right? And so when you see the delta, you want to be thinking big, right? Average over some length of time. And when you see the small d, then you want to be thinking, well, that's instantaneous, so that's going to be some very small fraction of it. So let me show you what the concept is, and then we'll get into describing it a little bit more. So the concept, I think, is sort of well shown on this. So suppose I have a graph that has some function associated with this. Is pretty close to a square function. I honestly don't know what it is. And if I'm interested, that I can find the slope, or the rate of change between 2 points, right? So if this is a displacement versus time graph, that slope is going to tell me velocity. And if I'm interested in 2 points between my first and my mth point, that I could find the average velocity by just drawing a straight line between those 2 points and then finding what the slope is, right? So the idea with calculus is, well, say I'm interested in the velocity exactly at one point, at point F. Well, what I can do is I can make that distance between them smaller and smaller and smaller. Right? And as I make that distance between them smaller, right, it's taking a limit, so as things get smaller, eventually I get to the point, well, is this essentially a tangent line? Right? So this is telling me the slope at this single point in time. And this is all the derivatives are doing. This is all that the calculus is doing for us, right? In this case, I'm figuring out, well, what is the slope at a particular point in a curve? What is the tangent line there? And I use these limits, so I take a really small section, right? So I call this dt here. So if this is time on my x-axis, this distance there, that's my dt. And I'm looking at, well, how does x change, or how does my position change with respect to time? And so this is one way of saying, well, this is going to be my derivative, or this is going to be my tangent line on this curve, right? So I'm finding the slope at a particular point. We're going to have the printer go for a minute, and then I'll get back to you. So, yeah, sweet. Okay, so we're going to have a handful of ways of looking at this, and let me just give you a couple of examples, maybe first, and then we'll put a general rule to it. So, a couple examples, right? So if I had, in fact, a square function, so if I had something where, I don't know, if I had displacement and time that was going at a function. So this is accelerating, say. Right, so my velocity, my rate of change to displacement over time, is increasing as I go. Right? So, say this is a square function. So, if I was to represent oops, if I was to represent position, it'd be related to, I don't know, the square of time. Right? So at this point here, I can get position, I take time, I square it, and I get position. This point here, I take time, I square it, I get to position. I take time, I square it, and I get to my position. Right? So this is a function that represents this, this relationship between displacement and time. And in this class, whenever you see a function, you want to be thinking about the printer. So that can keep going. Okay, so whenever you see a function, you want to be thinking about calculus. So it turns out that if I was to take this point and plot figure out what the heck. If I was to take this position and plot a tangent line, and then take this position and plot a tangent line, I would see that steadily increases at a regular rate. And it turns out that my velocity, the function for my velocity, so my velocity at position t is going to be 2 times the time. So I'm not going to go through a proof of this, right? You'll get to that, I think, hopefully in your calculus class if you haven't already. But I'm going to have two things. So notice I'm going to write my position at time point t. Right? That's a function. It's going to be t squared. To get to velocity, velocity is going to be the rate of change of position with time. So it's going to be the rate of change at my position. It's a function of time. Or I can write this way, it's going to be my rate of change of t squared, and it turns out this is equal to 2t. Right, so notice what we're doing. We're saying, well, I've come up with a new function where I can plug in t and then now tell me velocity. So at 2 seconds, my velocity is going to be 4 meters per second. Where am I going to be? Well, heck, I plug in 2 seconds. And I know my position at that time point is going to be 4 as well, 4 meters. So I'm going 4 meters per second, and I'm at the 4 meter mark. Right? As I get to the 3 times second, my velocity is now 6 meters per second, and my position now is going to be 9. Right? So this is how we're going to use derivatives. Derivatives are giving us the slope, so it's telling us the rate of change of things. And we're going to go from one function, usually to another function. So this is called the power rule, and we're going to use this a lot. So let me give you a couple of other examples. Let me give you a couple other examples, and then I'll switch videos and go to a different one. So if I had a different function, say I had my position as a function of time is equal to, I don't know, 3 t squared. Well, very similar, right? So if I wanted to find what my velocity is as a function of time, right? So I just plug in time and I could tell position, I could plug in time and find velocity. I'm going to take the derivative with respect to time of this function. Couple key things. So I'm going to pull a constant out. That's not going to be affected. And then I'll have this t squared, which is going to be 2t, and I'll end up with 6t. Another brief example. So if my position function is 3t cubed, then my velocity function, or the rate of change of 3t cubed, in this case, I'll pull a 3 out, and the derivative of t cubed is going to be 3t squared, or 9t squared would be the answer. Hopefully you see a pattern, right? So to take the derivative, I'm going to take the exponent, multiply it in front. Oops, take the exponent, multiply it in front, and then subtract 1 from the exponent to get my new exponent. So this is the power rule. And we're going to use it a bunch. One more example. Let's say I have 1/4. So my position with a function of time This is going to be 1/4 of, I don't know, t to the 4th. And then my velocity, which is going to be this is my instantaneous velocity, right? So this is velocity at any time point. So I can plug in time and figure out what my velocity is going to be the rate of change of that at that time point, right? So it's the slope, the tangent line at the time point of this thing. So I'm going to do the same process. So I'm going to take this exponent. I'm going to multiply everything by the exponent and then subtract one for the exponents to get the new one. So again, I pull the 1/4 out. It's constant. It's not part of this. It's not changing. And I'm going to have t to the 4th now is going to become 4t to the 3rd. And I'm left with just t cubed. So if I have a position function that looks like this, my velocity function will look like this. And we're going to go one further, right? So and the rate of change of velocity gives me acceleration, right? So I can take the derivative or see what instantaneous rate of change of velocity is. And this is going to tell me acceleration. So we can do this, right? So the rate of change with respect to time of t cubed, well, I'm going to multiply by the original exponent and then subtract 1 to get my new exponent. I'm going to have 3t squared. Anyway, power rule, most useful thing in calculus and physics, so hang on to it. I'll get you some practice with it in just a minute. Bye.